So we've all dealt with reflection before. Most of us have a mirror in the bathroom, or we run into mirrors almost every day, so we can certainly admire our lovely faces in the mirror. Let's talk a little bit more about the physics of reflections. So first up, you'll see I have two kind of pictures here. They're of the same spot, or roughly the same spot, and you'll notice there's a slight difference. Like you notice the water is very still here, smooth, calm. The reflection's very crisp and clear. But then we have like a lot of ripples in this second photo, probably like a small wind passing by. It's really ripply. It's really hard to see the reflection. Like you can kind of see bits of it here, but it's not clean. It's not crisp like this one. So we want to look at we're going to talk a little bit about why that is, but then our focus is going to be more on this cleaner reflection. So first up, what we know is that if our medium is uniform, so there's no changes in local density, we know light travels in a straight line, which we've already said is referred to as rectilinear propagation. So if we have light that falls on a flat surface, like a mirror, a plane mirror that we're very used to dealing with, it's going to undergo what we call specular reflection or regular reflection. For our purposes in Physics 30, reflection's good enough. And this is the gist of what's going on in specular reflection. You have all these light rays coming in parallel to one another, and then you have all of these outgoing light rays parallel to one another. This is what gives you an image like this. Everything is nice and clean and crisp. Image is really, really easy to see. It's nice and clear. Now, the other type of reflection that we could have is this thing called irregular or diffused reflection. So we still have all of our light rays coming in parallel to one another, but then because of the unevenness of the surface and obeying the law of reflection, like the angle in equals angle out relative to some normal, you'll notice that the outgoing light rays are nowhere near parallel to one another. They're kind of all over the place. And what this is going to do is this is going to lead us to a distorted image, because these reflected light rays, these are the ones that are going to be coming back at our eyes. And because they're all over the place, they're going to lead to an image that looks a little bit like this. Our focus in Physics 30, however, we just want to deal with regular reflection. Both of these still obey the law of reflection. This one's just a little bit more complicated, so we can kind of save that one for, well, we're not going to do it, but you can save it for another time. Maybe in a university course. So we just talked about that word reflection. We're going to talk about the law of reflection. You've likely already seen this. We're going to go through it again very quickly. But the big thing with this electromagnetic radiation unit, there's a lot of terminology. So we have some terminology that's associated with this diagram. So this whole sketching of our light rays kind of coming in and going out, this is referred to as a ray diagram. It just basically shows how light is interacting with the system. So we have an incident ray. The incident ray is going to be the incoming beam, the outgoing beam that's reflected from the surface. This is what we refer to as our reflected ray. The point of incidence is where the beam, the light ray, contacts the surface. So this is our point of incidence on the mirror. We have our angle of incidence. So that is going to be, or actually before I get to that, we have this thing called the normal line. So the normal line is going to be drawn 90 degrees or perpendicular to your reflective surface. The whole purpose of the normal line, this is just where we're going to base our measurements off of. So that normal is 90 degrees to the surface. We're going to talk a lot more about the normal a little bit later. So the angle of incidence, that is going to be the angle between the incident ray and this normal ray. The angle of reflection is going to be that angle between the normal and the reflected ray. And then we also talk about a plane mirror. So plane mirror, it's going to be a smooth reflecting surface. Key for us though, it's going to be flat. Curved mirrors is something we're going to study in depth very, very shortly. Now, we know from our studies, probably in like science 7, 8, or 9, somewhere in junior high, we know that the angle of incidence is going to equal the angle of reflection. So that angle of incidence with respect to the normal, that is going to equal our angle of reflection with respect to the normal. This is known as the law of reflection. And of course, we can always put that in words. We could say, as it said here, angle of reflection is equal to the angle of incidence and is in the same plane. So the same plane just means like you're not going to have this light ray coming in and then this is going to bounce out towards us. If this is in the two-dimensional plane, this is kind of in the XY plane, the reflected ray is also going to be in the XY plane. Now, that's great that we can have it in words. More succinctly, we like the math. Theta I equals theta R. Nice, quick, and simple. So the special case happens to be if your angle of incidence is 0 degrees. So that's going to be the case where the light ray, it's coming in perpendicular to the mirror, so kind of along that normal. Well, if it comes in perpendicular to the mirror, it's also going to be reflected out perpendicular to the mirror. It's going to be reflected on that same line. I just sketched them side by side, but they would be one over top the other. So that's kind of our special case, but it still obeys the law of reflection, like theta in equals theta out, 0 degrees. So when we're talking about mirrors, there's going to be two important things. There's going to be the object. So this is going to be the thing. This is going to be like the actual physical thing in question. So for example, if you're looking at yourself in the mirror, you, the actual physical you're the object. The image is what you see in the mirror. And what we want to do is we want to distinguish between two different types of images. So leading into that point, if you look at yourself in a mirror, so here's kind of your eye. Sorry, here's your eye. It's looking at the, oh my goodness, sorry. Here's some object that you're looking at in a mirror. So this object, what it's going to do is its light rays emanating from that object are going to hit the mirror and they're going to reflect back to your eye. Now the thing is, your brain is not going to interpret the object being here. What it's going to see is, okay, these light rays are going to the mirror, but they don't quite converge it. They don't meet at a single point. What your brain wants to do is it wants to take those light rays and extend it behind the mirror until they actually converge, because you can see they're kind of getting in closer and closer, and then they converge on this point. So what your brain is going to interpret with that object, it sees that object, but it thinks based on these rays converging behind the mirror, it thinks that the object is behind the mirror. So when you look at yourself in the mirror, your brain thinks that that image of you in the mirror, it's actually physically behind the mirror. It's kind of looking back at you. But we know that's not actually true. What's happening is your brain is processing where it believes the object happens to be, where it thinks those light rays are emanating from, but they're not actually emanating from that point. Because in the case of an object in the mirror, the image is not actually behind, there's not actually a physical object behind the mirror. That object is in front of the mirror. So when we have this kind of trickery going on, when that image is not where we see the image, if the image is not in kind of the same area where the object is, we would say that this is a virtual image. This is being formed by rays that are not actually real. Or basically, it's kind of like your brain playing tricks on you. You think the object is there, but it's not actually there. And kind of to test if something's virtual, we'd imagine placing a piece of paper where the image is, and then we'd ask, could we see that paper? So if we looked at ourselves in the mirror and we see our image, it looks like it's behind the mirror. If we placed if we placed a piece of paper behind the mirror, we wouldn't see that piece of paper. So what that tells us is that that image we're seeing, it's virtual. The light rays are not actually emanating from behind the mirror. They're emanating from somewhere else, the actual physical object. In contrast to that, we have this thing called a real image. So in a real image, the actual light rays are what's hitting your eyes. So for example, if you looked at, say, I don't know, I'm just thinking of an apple for some reason. So you have an apple on a counter. If you're looking at the apple directly, the actual light rays from that apple are hitting your eyes. That's a real image because the image that you see corresponds to where the physical object happens to be. You're seeing the real light rays from the apple approaching your eyes. And of course, we could do the standard test. If you put a piece of paper where the apple is, would you see the piece of paper? The answer is yes. That is going to tell us it's a real image. So we can usually say that real images can be projected on pieces of paper or they can be projected on screens. So you only have two choices. Your image is either going to be real or it's going to be virtual. The real virtual thing, it really confuses people. And, this wasn't the world's greatest explanation, but hopefully as we work through this unit, you'll start to kind of see the distinguishment between the two. So just the last thing I want to talk about, when we're talking about characteristics of an image, there's kind of four principal characteristics that we can look at, and we're going to define these a bit more in detail later. We can look at what's called the image magnification. What we want to see is, we want to see how much bigger or smaller the image is relative to the physical object. So the magnification can be positive or negative. We'll talk about that later. And you have three choices for magnification. Your image can be the same size as the object. It can be bigger, enlarged, or it can be smaller or diminished. Attitude has to deal with the orientation characteristics of the image. So this basically means what is the position, or what's the orientation of the image relative to the object. If they're both upright, we would say that the image is upright or erect. Whereas if the one image is pointing up, if the objects say upright and then the image is inverted, then we're going to say that that image is inverted because they're inverted relative to one another. Or we could say it's upside down. Position actually just tells us where physically relative to our mirror that object happens to be. Is it 5 centimeters in front of the mirror? Is it 10? This is something we're going to talk about more in depth when we start doing the math. And then the type of image, we just kind of discussed this part. Is it a real image? Is it a virtual image? But this is one it's going to be easier to see this when we start doing the math and when we do the ray diagrams.